This class starts description about the third fundamental configuration of switch mode power converters, which is the buck boost. So in order to do that, let me share my whiteboard. Okay, so you should see in this whiteboard the topology of the buck boost. Okay, now we have the voltage within, and then we have the switch. We have an inductor L, which is in parallel to the power flow. So one of its terminal is connected to the reference terminal here. Then we have the diode and the output port of the converter. Okay. So as you can see here, there is the same components that we have for the buck converter and the boost converter. Okay. So arrange it in a different ways. We learn during the next lectures that the buck boost has this specific name because it is exactly the cascading topologies configuration made by the buck followed by a boost. Okay? As you can see, this is can be understood if you look at the input port. Okay, if the input port, you can see that you have a switch which is say connected to V in. This is exactly what happened in a buck. It is the buck converter that has the switch in series with the input port. And what is the consequence of having a switch in series with the input port? First of all, this switch is an I-side switch. Okay, so this is I side switch. I-side switch means that in order to drive it, specific gate driver circuits that are called I-side drivers are needed. Okay, they are expensive, they are, say, a little bit more complicated, but anyway. So, another consequence of having a switch in series with the input is that if you have at the input side some over voltages, okay, so that means that the input voltage exceeds the nominal value for a short time interval due to some, say, for example, interference due to apparatuses and equipment that are in the same environment, the buck boost converter, then these over voltages, let's say, is shared to the drain connectors, drain terminals of this buck. So the buck boost switch experiences all the other voltages that you can have in the input side. So that can be, say, a little bit dangerous. So you have maybe to think some way to protect it. Remember that C-in is the simplified version of what is an input filter. Okay? So this is something that can be, say, reduce the voltages at the input side of the converter. In that case, it means that the input filters is, say, to be designed also for this occurrence. MOSFET at the input side means that the current that flows to the switch is not a smooth current, is a pulsed current. And so, again, that means that the input filter is electrical stressed, okay, because the current which flow here is a pulsed current. But there are also some benefits of having a switch in that specific position, that means in series with the power flow. For example, we can control the inrush current. Remember the problems of the inrush current when you turn on the converter, that suddenly in the very short time interval following the start up of this converter, then we have to manage a large flow of current that goes into synod capacitor because it's completely discharged. Okay? So that means that you have a typical high peak of current during this time interval, which is very short during this up timing. So having an high-side switch in that case, in series with the input means that I can use this switch in order to act in a soft start way, so increasing the duty cycle slowly, in order to say manage the input current. So this can be also a benefit. Okay, benefit means that you can have a good control of inrush current. Another benefit is that the transistor in series with power flow can help to control a short in the output side. If you have a short at the output port here, okay, then in that situation, there is the same behavior. The voice is disturbed. I don't know what to say because here I'm completely alone here. The audio is quite bad. Okay, I can speak louder, but I think that this means that I have something bad with my equipment. I don't know what to do. Can you change the mic? Okay. let me do a try, okay? Let me do a try. Can you hear me? Can you hear me now? Can you hear me now? Can you hear me? Can you hear me? Can you hear my voice? Yes? It's better now than before? It's better for you? Better? So I can continue? Okay, I can continue in this way, okay? Okay. Okay, thank you for your feedback. Okay. So another positive effect of having the transistor in series, like in this way, is that you can control what happens when you have a short circuit at the output port. Okay, if the output port is shorted, then you have a huge amount of current flowing in the output side of your converter, but then you can left open the switch, and this means that this current is suddenly stopped. Okay, so another positive effect is that you can control and manage output curves. Okay. By the way, the input side is look like that of a buck. What happens looking at the output side? If you look at the output side, then you can immediately say, verify that you have a diode here, and so this is the same that you had in the boost converter. Okay, the polarity of the diode is not the same, but anyway, you have a pulsed current flowing to the diode. So that means that the current flowing through the output capacitor C0 is, let's say, something that should be support a high level of stress. So in these circuits, in the buck boost converter, both the input side and the output side should support a very large amount of electrical stress. So the input and output capacitor should be large enough to support a large level of root mean square value of the current flowing to them. So that means that you can have possibly also electromagnetic compatibility issues, both at the input side and the output side. Remember that for a buck converter, that happened just for the input side. For the boost converter, this just happened for the output side. Now the buck boost converters that, let's say, is a merge of the buck input side and the boost output side have, let's say some kind of problem both for the input and output side. Okay. Another consideration that I can say now, but then we can be some explanation of that later in this course, is that the buck boost typically is operated in DCM. Okay, so we can say that typically it is operated in DCM. Why? Because, as I said before, the buck boost is the combination, is the merge of the buck and the boost. Remember that the boost cannot be operated easily in CCM due to the, say, transfer function, the closed loop, the loop gain of the closed loop system that has some problems in, say, having a very small phase margin, okay? Having a very large phase margin. So this is the same for the buck boost. The buck boost in CCM has a loop gain with what is called a right half plane zero. And when you have a transfer function having a right half plane zero, meaning that you are, say, reducing your phase margin. And so that means that easily you can go in instability. Okay, so typically no CCM, but it is operated in DCM. But it is something that we can learn in successive lectures. Okay. Anytime you have some properties that are some inherence of the buck, or sorry, the boost, in that case, you can have the same, say, features. Okay, the boost, the features that you should operate it typically in DCM, okay, discontinuous conduction. So what happens in the standard operation definition? Okay, so let's start with the analysis of the continuous conduction mode that now you will understand that is a situation in which the inductor current is always different from zero. Okay, and let's start with the time interval that ranges, say, from 0 to the on, in which the switch is closed, the switch is on. If the switch is closed and we have all the usual simplification, in which we could say that an on switch is a short circuit, an open switch is, let's say, an ideal open circuit, that we can rewrite our circuit in this way. The switch is closed, so switch is on. Then you have inductor here. This is the input side, in which you have C in, and then you have V in. Okay, the switch is closed, so that means that the voltage across the inductor, which is VL, is exactly the voltage V in. Then you have here the diode. What happens to the diode? Then you have here the C naught, R, and then you have V naught. Look at the voltage across the diode, okay? The voltage between the cathode and the anode. This is VD equal to V in, which is the voltage across the inductor, minus V naught, okay? So, which is the basic characteristic of the buck boost? The buck boost has as a basic characteristic that the voltage V naught multiplied the voltage V in is less than 0. So that means that if you have a positive voltage at the input side, for example, with this polarity, okay, the output voltage has an opposite polarity. Okay, so the output voltage has a sign which is totally different between the sign is the opposite sign of that of the input side. Okay, so if the voltage V in with that polarity is positive, the output voltage is negative. Okay, so V naught is negative, supposing that V in with the polarity is positive. So that means that V in minus V naught is a positive voltage, okay, because the summation of two positive quantities. So the voltage VD is a positive voltage, means that is a voltage that is able to put the diode in off state. The diode is interdicted. Okay? The diode is off. Diode is off. If the diode is off, we can say cancel out from the circuit. Okay, so the circuit is exactly this one during the time interval, which is T on. As you can see here, the power provided by the input source now is totally devoted to charge the input inductor, okay, to charge the energy inside within the magnetic field of the input inductor L. So if you look at the voltage VL, the voltage across the inductor, this voltage is V in this time interval, which is T on. If you look at the current flowing to the inductor, which is IL, okay, IL is a current which has a positive slope. And the positive slope is VL over L, so it is V in over L, okay? It's easy to understand that in this phase, which is the T on phase, I switch is the same of IL, okay? I switch, the current through the switch is the current through the inductance L. The current through the diode is 0 because the diode is off. Okay? This happens during the time interval T on. This phase in which during T on we have the voltage at the input, the in, that is devoted to charge the inductor L, is also called the charging phase. Okay, this is the charging phase, and of course we are talking about the inductor. We are charging the inductor. Okay. So what happens when you have the successive time interval? So we can say T, that is from T on to Ts, so which is the period, the switching period of our waveform. In that case, the switch is commanded to be off. And so in our approximation, the switch off is an ideal open circuit. So we can say that switch off means open circuit. Then you have the inductor L. Here you have the input capacitor, which is the in, and then you have the diode. Okay. Not, and then you have the output voltage. The output voltage across R with that polarity is negative, remember. Okay. So the voltage across the switch is exactly V in. The inductor, before turning off the switch, has a current flowing through it, IL. Okay, the current flowing to the switch is exactly at this level, is the maximum current, I max. Of course, when you open the switch, the current through the inductor continue to be different from zero. The inductor does anything it can, say, try to maintain the same current that it has before switching off the switch. And due to this not null current IL, that now the diode becomes on, because it has to, say, makes possible the flow of the current. And so the diode becomes on because we cannot put to zero instantaneously the energy across the inductor L. So we cannot interrupt the current instantaneously if the current flows through an inductor. Okay, so if the diode is on, it means that the diode can be replaced by a short circuit. Okay, the diode is considered to be ideal, and so the current means the diode is a short circuit. So in that situation, which is the voltage across the inductor, the voltage across the inductor, VL, is the same of V naught. But remember that V naught in the buck boost is negative, say an opposite polarity with respect to that of the input voltage. As you can see in that situation, is the voltage across the output capacitors that make possible to maintain the output voltage to a constant value. Okay? Since in that situation there is no connection between the output and the input side of the converter, the output voltage VO is held to a constant value as an DC-DC switch mode converter by the capacitance voltage here, exactly as it happens in the boost converter. In the boost converter, there is during T off the situation in which is the output voltage across the capacitor that should be large enough to be constant enough to be maintain the output voltage. Okay? In that specific situation, which is similar to that of a boost, we have to also consider what happened during T on. Okay, during T on, as you can see here, again, there is a situation in which you don't have any connection between the input side and the output side. They are totally separated. This happens during T on, but as in the boost, it happens also during T off, in which the input side is separated by the output side. This is a specific feature of the buck boost. Okay? In the buck, this not happen. For example, in the buck, if you consider what happens in the back, during T on, in time interval in which the switch is closed, you have something like this. The switch is closed. You have here the diode, and you have inductor. Okay, and so the diode during T on is off, but you have a connection between the input side and the output side. Okay, so the power flow, they start from the input and goes to the output. So it happens in the back. In the boost, what happens in the boost? In the boost, during T off, the switch is open. The diode, which is here, is on. So this is open, this is on. And then again, you have a connection between the input side and the output side. So in the buck and the boost, there is a time interval in which you have a connection between the input side and the output port of the converter. In the buck boost, this never happens. Both in during T on and in during T off, always you have no connection between the input side and the output side. During T on, during the so-called charging phase, you have the input voltage, which is just connected to the input, the inductor L, okay? And so that means that you are charging the inductor L. In the second phase, which is during the off, the energy which is stored into the magnetic field of the inductor is provided to the output without any connection between the output and the input. This is a specific characteristic or a class of converter that are called indirect converter. Okay, indirect converter means a class of converter in which you don't have at any time instant direct connection, so galvanic connection between the input side and the output side. For example, this happens in the buck or in the boost, okay, as I explained here. Okay. Any questions about this? So what happens for the buck boost during the T off? Okay, during T off, the voltage across the inductor is V naught. So let me draw a waveform of the voltage across the inductor. This is, for example, T on, and this is the switching period Ts. So during T on, we have V in, and then during T off, we have V naught, and V naught is negative. And then the situation repeats periodically. What happens to the current? The current flowing through the inductor has a positive slope during T on, and the slope is a V in over L, as I said before. This is the slope. And during T off, we have a negative slope because now the voltage across the inductor is negative, so the slope is V naught over L, and which is negative. Okay. Remember that we are talking about CCM, so the current through the inductor is always positive. And we also discuss a situation in which we are in steady state. So that means that the input current is the same as the current you have at the end of Ts. We can define I mean the minimum current flowing to the inductor, I max the maximum current flowing to the inductor, and the difference between the two is called the ripple current through the inductor. Okay. Again, we are in the steady state. What does it mean, steady state? It means that you can apply the volt-second balance on the inductors. So across any inductors in steady state operation, you cannot have any DC value. Okay, no DC current can be applied to a steady state inductor. So that means that the two areas here, positive and the negative area across a period, should be the same. So we can apply this kind of balance expression for steady state voltage across inductor, saying that during the duty cycle D, the voltage V in multiplied D should be, and this is the area that you can have here, so let's say A plus, is the same of the area A minus, which is V naught, which is negative, so minus V naught is positive, 1, okay, because 1 minus D is the remaining period you can have in a cycle. Okay, so try to solve this expression, which comes directly from the volt-second balance of the inductor, to derive the output voltage V naught. Okay, V naught is minus V in multiplied D over 1 minus D. From this expression, you can say that V naught over input voltage V in, and this is also called the conversion ratio in CCM, M, is D over D minus 1. Okay? So this is the conversion ratio. This conversion ratio, since D ranges from 0 to 1, of course, M CCM is less than 0, is negative. Okay? So that means that you have an inversion of polarity between the input side and the output side voltage. So that is very important. This occurs for the sign. Okay, the output polarity is the opposite of the input polarity of the voltage. But what happens about the magnitude? The magnitude of the output voltage, depending on the value of D, can be, let's say, larger than 1 or less than 1. So if you look at the magnitude, V naught, absolute value, can be larger than V in, or it can be lower than V in. Okay? Opposite polarity, but the magnitude can be whatever you want. If you want to discuss this graphically, then you can have the MCCM versus the duty cycle. Remember that M is D over D minus 1. And so when the duty cycle is 0, M is 0. Okay? When the duty cycle is 1, when the duty cycle is 1, you can get infinite value. So you have something like this. Okay? This is a curve that graphically explain this conversion ratio. Okay, of course, you can have 1 here. So as you can see, you can have the output voltage that in magnitude can be higher than 1 or, let's say, less than 1. Okay. We already found out something similar in the boost. Remember what happens in the boost. In the boost, we have the conversion ratio, which is, say, something like this, okay, in the boost. But in the boost, this curve starts from 1, and then from the cycle 1, it diverges. Okay, something like so. The output value, the quantity in absolute value is always greater than the input voltage. Okay, here the curve starts from 0, so it means that you can have output voltage that can be in magnitude higher than V in or less than V. In common, these two curves have the fact that when the cycle is 1, they diverge. Okay? In the boost, it goes to infinite. In the buck boost, it goes to minus infinite. Okay? So remember what we said about the boost. This is not this is in practical circuits is impossible. Okay? What happens that due to the fact that you have some effect due to parasitic elements, the real curve is something like this. So you have a maximum possible duty cycle, and then if you overcome this possible duty cycle, then the circuit does not operate as a boost. Okay, so you have the maximum. And the same happens here. Okay? The same happens here, meaning that it's not possible to reach something which is infinite, okay, then in real practical circuits, what you obtain when the duty cycle is 1 is that you cannot have any output voltage. Okay? This is quite understandable if you look at the circuits. What does it mean duty cycle 1? Okay? Duty cycle 1 means that if you look to the circuit, okay, which is this one, okay, duty cycle 1 means that you are in a period the switch is always on. And if the switch is always on, the situation is always this one. And the situation stays, say, forever. It means that the output voltage V naught should decrease to 0 because at a certain instant, the output capacitor is totally discharged to the resistance, okay, to the load, and that the output voltage is 0, meaning that the conversion ratio M at the end should be 0. Okay, so you should understand that this situation always leads to the fact that the conversion ratio with V equals 1 should go to 0. The same happens for the conversion ratio of the boost. Okay, so you can discriminate within an ideal conversion ratio what is, say, in practical you can obtain. Okay. Let's come back to the current through the inductor, okay? Because as usual, through the analysis of the current through the inductor, we can understand which is the critical inductance to operate our buck boost always in this CCM or in DCM, okay? The usual analysis that we already have, okay? So let me rescale the axis in duty cycle, okay? We have D and we have 1. The inductor has a current which is something like this. So we have I minimum, I maximum, and then you have the ripple. Let me redraw just for, say, my simplified analysis, a part of the circuits, okay, a section of our buck boost circuit, okay, which is that composed by the switch, the diode D, and the inductor. So for a moment, I do not consider the input capacitance, the output capacitance, and the output load. Okay, just this network here. This is the node that we can call as common between this node is common between the switch and the diode. At this node we have the switch current, then we have the inductor current, and here you have the diode current. So the Kirchhoff current law says that the inductor current is equal to the switch current plus the ID current. Okay. The same Kirchhoff current law can be applied to the average values of this current. So we can say that the average value of IL, that sometimes I call in this way, is the summation of the average value of the switch current plus the average value of the diode current. Okay, because Kirchhoff current law holds for the average values. Okay, which is the average value of the switch current. But the switch current, okay, now it's interesting to put here the input capacitor. We are in steady state. We know the charge balance law for capacitors. That means that no DC current can flow through steady state capacitor. So no DC current can flow here. So that means that all the DC components you have in the switch flow here. But here you have the input side. So this is the input current. So the average switch current is the same of the input current, which is the average current flowing through the diode. Again, we can say that we have C naught, but through C naught in steady state, no DC current can flow. So the DC current that can have here is null. So all the DC average value of the diode current flow to the output side, flow through the resistor. So here you have I naught. As you can see, the direction of the output current is opposite to the direction of the diode current. So we can say that ID average current is negative I naught. Okay. So the average value of the inductor current is the input current minus the output current. So what is the input current? In order to derive the input current as a function of the output current, we can apply the condition that always you can have in lossless circuits. My analysis here, as a basic assumption, is a lossless circuit, so we cannot have any energy loss. Okay? So that means that output at the input should be always the power that you dissipate at the output side. So that means that V in multiplied I in is equal to V naught multiplied I naught. So from this expression, we can derive that I in, the input current, is V naught over V in multiplied I naught. V naught over V in is the conversion ratio. So it is M CCM I naught. So let me write this condition here. I in is equal to D over D minus 1 I naught. Okay. So if I have the average value of the current IL, this is I in minus I naught, and this is I naught multiplied d over d minus 1 minus I naught, okay? Because I in is due to this expression. So I naught multiply 1 over d minus 1. But I naught is v naught over r 1 over d minus 1. Okay, so this is the expression of the average current flowing through the diode. Okay, so we have an expression for this average current here. Now we have this average current. What about the ripple current through the inductor? The ripple current through the inductor should be derived by looking at the slope. For example, this slope here, which is V in over L, or the slope here, which is V naught over L, and take into account the time interval in which this slope happens. Okay, V naught over L is across 1 minus d. V in over L is the slope from the time interval, which is d. So delta IL should be defined as V naught over L 1 minus d fs. V naught is negative, so we have to put a minus here. Or you can have V in over L d divided fs. The same. So now we have the ripple and we have the average value. We can compute the maximum current. The maximum current is average value and then plus delta IL divided by T. So this is V naught over R divided to d minus 1. Delta IL, suppose you consider this expression is minus V naught 1 minus d over 2L. I minimum should be average value minus f the value of the ripple current, so it is V naught over R d minus 1 plus V naught 1 minus d QLF. Okay, so using these two expressions, we can derive the maximum and the minimum value. Remember that this situation is evaluated for CCM. So if you look IL versus T, this happens for a situation in which you have a totally positive inductor current, which is the boundary between the CCM and DCM, is a situation in which you can increase the load and then you have this situation here, which the minimum current is 0. Okay, so this is typical for CCM. But this one is what is called critical conduction mode or boundary conduction mode. If you increase the load too much, starting from CRM, then you go in DCM. So that situation, which is the critical or boundary conduction mode, is when the minimum current is 0. So that means V naught over R d minus 1 plus V naught 1 minus d divided Q L Fs is null. From this expression, we can derive a critical inductance. And this critical inductance is R 1 minus d square divided 2 times Fs. If you increase the inductance over to this value, you can operate in CCM. If you have an inductance which is lower than this critical inductance, then you can have operation in DCM. Okay. Again, as we did for the other converters, we can have two dimensionless parameter, which is K, Q, Fs over R, and K critical, which is now 1 minus d square. Okay, so you can have that in the critical conduction mode, you have that QFS multiplied L divided R, which is exactly K critical, K is equal to K critical. Okay, so at CRM, K is equal to K critical. As we did for all other converters, let me draw this the graphical representation versus D of K critical, which is 1 minus D square, so it's something that is goes to 1 when the duty cycle is 0, and is 0 when the duty cycle is 1, so something like this. Okay. And we have to compare K critical to K. So K depends on L, depends on R, depends on the switching frequency. For example, if you have K, which is, let's say, in this way, so something which is in between 0 and 1, then here, when K is the same of K critical, you are in CRM. If you have K, which is larger than this value, you are operating the buck boost in CCM. If you have a K which is less than this one, you have DCM. Okay, so in that situation, for a specific duty cycle, D star, okay, you are operating your buck boost in DCM for the lowest range of duty cycle, and in CCM for the highest range of duty cycle. What happens when you have, as it always happens, a variation of duty cycle between a minimum value and a maximum value. If you have the minimum and the maximum, and this is K critical. Suppose that you want to operate your buck boost always in CCM. If you want to operate your buck boost always in CCM, you have to be sure that, for example, your K is, let's say, this one, okay? This K to stay CCM for the duty cycle interval the minimum and the maximum. If you want to operate in DCM, if you want to operate in DCM, then you have to be sure that your K is this one to stay DCM, okay? Because in that situation, you are always considering operating points that are lower the K critical card. So that means that you can have, say, always DCM operating mode. So, in order to operate in DCM, you have to consider the Dmax, okay, in your expression, for example, for the inductor, and you want to operate in CCM, you have to consider the minimum. So, let me redraw L should be larger than maximum load 1 minus d minimum square over QFS to stay ACCM. Okay? Or L should be less than L minimum 1 minus D maximum to stay DCM for the entire interval, D minimum, D maximum. Okay, so the conclusion are always the same. Okay, you have to put inequalities in order to find out the inductor that involves the maximum resistance or the minimum inductance, depending if you want to stay higher or lower than the critical curve. Okay? Nothing more than this. You have always the same reasoning here. You have questions about this, say, derivations? I think that now at this point you should be, say, quite you will quite understand which is the correct procedure for each convergence. If you have problem, you can say something. Okay. We are discussing CCM buck boost, and so we can again list the parameters that are typical for this CCM operating mode. Okay, for CCM buck boost, we have okay. I have a questions. Desario Federico. Sorry, Prof. We said that if K is larger than K critical, we are in CCM. So to be always in CCM, it should be K less than critical maximum. Let me again discuss this point. Sorry, what is this? As you can see that, are you agree that when K is K critical, we are in at the boundary, okay? And if you want to stay CCM, it means that you should be considered that K is larger than K critical. Okay. So if you want to stay, for example, in that specific situation, which you know from the beginning that your duty cycle is, let's say, bounded within the minimum and the maximum. If you want to stay in CCM, you have to put a K which is always higher than the red card. So that means that you have to consider the minimum as the duty cycle you have to consider in this description. Okay, so that means that you have to be sure that you always be in CCM. Of course, you have to consider the minimum because this gives you the maximum possible numerator in this expression here. So if I said that L is maximum of the possible numerator, highest possible numerator, I quite to be sure. This is another way to be think. This is the reason why I have to put here maximum R. Okay. In all possible situations I can have, I have to be sure that L is higher than the K critical card. So you can get this by having the maximum possible numerator. Okay. So it means the one minus the minimum gives you the maximum value, and R max gives you the maximum value. Okay. If you don't want to reasoning about the card graphical one. I hope that this helps you. So classical parameters is the audio susceptibility. Audio susceptibility is the derivative of the output voltage respect the variation, the small variation of the input voltage. And this is always the conversion ratio. This happens for all the converters. Okay? Always the audio susceptibility is the conversion ratio. In this way, in this case, is D divided D minus 1. Small signal output resistance. This is the small signal variation of the output voltage with respect to the output current, and this is null because the output voltage has no link to the output current or the output resistance. Okay, the output voltage is simply V naught, which is V in multiplied V over V minus 1. So it is not included in this expression the resistance R, the output current I naught. So if you get the derivative of this expression in terms of I naught, you can get 0. So that means that it's a good regulator of the output voltage. Then you can have the gain. The gain is defined as the variation of the output voltage in terms of the small signal variation of the control quantity, which is the duty cycle. And so you have to put the variation in terms of duty cycle of V in T divided T minus 1. V in is a constant in this derivation, and then you have minus 1 over D minus 1. So let me have a little bit of manipulation. So we have that gain is minus V in over d minus 1 square. Remember that v naught is v in d over d minus 1, okay, for the buck boost. So we can replace v in with this expression here. So v in is v naught d minus 1 over d, and then you can put this expression here, and then you have v naught over d minus 1. And this is the gain. So the gain depends on the duty cycle, okay? Is 0 when the duty cycle is 0 or 1. And when you have duty cycle 1F, this gain is the maximum, okay? And then also depends on the voltage V in. You can see here. We can use this gain when you say talked about, we will talk about the closed loop control of this. What happens to the other electrical quantities in these circuits? We saw that we have an inductor current, IL, and this inductor current has the classical CCM waveform, which is this one, over Ts. Let me redraw the circuits of the buck boost, which is this one. So I just say I have this current here, which is the plotted current. What does it mean, for example, for say the diode current? Let me show in blue. Diode current. The diode current is the same of the inductor current when the switch is off. The switch is off during T off, so T on and Ts, so the current is this one. Okay, it's the same current you can have in an inductor, but only when the diode is on. Okay, when the diode is on, you are during T off. This is the diode current. Okay, and so in that case, what is the average current value? This current is IL, and we know that this is the input current. How can we say about the, for example, the average current through the diode? The average current flowing through the diode, since no average current can flow through the C0 capacitor, the average current through the diode is the same of the I0 current. So IV average current is the same of the output current. Note that we have a minus signs because the direction of the two currents is opposite. Okay, so this is what happens. So the average current is minus V0 or negative V0 over R. What about the root mean square current through the diode? The root mean square current of the diode is not useful for computing the, say, the conduction losses, but it is useful to derive the root mean square current of the C0 capacitor. So we can compute now. The root mean square current of the diode can be computed by using the classical flat top approximation. So I can approximate the ID current by using, say, a flat top. So I considering here a value which is the average value between I minimum and I maximum, the mid value, which is IL, so the average value of IL. So I can approximate the ID current not as a trapezoid, but as a rectangle. And so by flat top approximation, I can say that ID root mean square is about IL average value multiplied 1 minus d square. Okay? IL average value is I in. And remember what I said. Let me change the page. ID root mean square is IL 1 minus d. IL average value we computed before is V naught over R d minus 1. Okay? So you can replace this value over here, and then you can have that ID root mean square current is V naught over R minus d. Okay, V naught is negative, 1 minus d is positive, so you can get V naught absolute value in order to get positive value. Okay, so this is ID RMS, which is the maximum voltage across the diode, which is the maximum reverse voltage across the diode. But when the diode is off and the switch is on, the voltage across the diode is V in minus V naught. Since V naught is negative, it means that this voltage is positive. Okay, so the maximum VD voltage is, say, V in maximum value minus V naught. So the breakdown voltage of this diode should be larger than the summation of the input and the output voltage. So it should be quite large, this value, if you think. What happens to the switch? The current flowing to the switch is the same current of the inductor when the switch is on. So it is a waveform that is the complementary waveform of the diode current with respect to IL. I switch is equal to IL when the switch is on, so during T on, and then is 0. During T on, I minimum, I maximum. Okay? Which is the average value of this current? The average value of this current is something that is here, is the input current. Okay? We already derived this expression, and this is V naught let me check if I computed correctly, because we computed before. Check the previous computation. Is here. So there is a bit here. And so it is this one. Okay, it's correct. IL average value is V naught over R divided V minus 1. This is the average value of the inductor, okay? I'm talking about the switch. Okay, I missed a D in something here. Okay, let me check. IL average value here, you have a B. Okay, so that means that you have a B here. Okay, should be corrected in this way. And if you look here, you have the switch current. This is V naught over R 1 D minus 1. This is the input current, okay? The average value of the input current, which is the maximum voltage across the switch. The maximum voltage across the switch is the voltage across the switch when the switch is off. And when the switch is off, again, we have V in minus V naught. So again, you have to buy a transistor which has a maximum breakdown voltage which is larger than this value. So this value is quite large, okay, because it's a summation of the input and the output voltage. What about the root mean square value? The root mean square value of this current is, again, something that we can compute by looking at a flat top approximation. So we can approximate the current as a rectangular waveform, having something which is top at IL average value, and so the switch current RMS value is about IL average value squared, which IL average value is computed as before. Okay. So for today, I think that we can stop here. We can continue tomorrow. Okay, tomorrow morning at 8:30. I have no answer, no news about the laboratory. Okay, so that means that we are waiting for news for next Friday laboratory. Okay, I think that always even the booking procedure is blocked for you students on the portal. I think that is what they say to me. Okay, so but I think that the situation can be, say, unblocked, can be something can be, say, done in the few hours, maybe, say, a few days, but before Friday, okay? So let me say hello to you. If you have questions, you are here to answer your questions. Not, you can disconnect, okay? Okay, thank you for your attention, and see you tomorrow morning, 8:30. See you, bye, thank you.